So we've now got an idea how you might describe an equilibrium reaction in terms of its Kc expression. But the rest of the rest of this topic concentrates on how you might influence that yourself and change the equilibrium. So in other words, if we got A going to B, yes, we can study what the Kc expression is. Yes, we can describe the equilibrium as being on the right hand side or left hand side. But now we're more interested in, well, how would we affect that ourselves? How can we make it go from A to B, or more go from B to A? A really important concept in actually changing the position of equilibrium is Le Chatelier's principle, named after a French scientist. His principle states, if a change is made to conditions of a system of equilibrium, then the position of the equilibrium moves to oppose that change in conditions. So it's a very kind of general definition or principle, but essentially whatever you do to a system, your system tries to do the opposite in response to that. You never really have to worry about why or how it does that, as if it has like a mind of its own. It's kind of like things like probability or like thermodynamics. It's only really important you're able to apply that definition to different reactions. So keep it as, if you do something to an equilibrium, your equilibrium will try to do the opposite to cancel out that change. There are three types of change you have to know about to be able to predict the effect of. It's concentration, temperature and pressure. So look at each one in turn. First thing you can do to an equilibrium mixture is to change its concentration of one side or the other. So if we just jump down here to this example, if we have A going to B and B going back to A, and they're now in dynamic equilibrium, so the concentrations of those are fixed. If I then affect that equilibrium by adding or taking away one of those reactants or products, that will affect the position of the equilibrium. First type of change I could do, if I actually added more A into equilibrium, so literally pumped a bit more in, that would increase the concentration of A. That changes the equilibrium, and according to Le Chatelier's principle, whenever I make that change to the equilibrium, the system moves to oppose that change. So if I've increased A, the system wants to decrease A. The only way it's able to decrease A is to turn it into B. So that will cause the reaction in the forward direction from A going to B to speed up, or in other words, be favoured, and that will cause the equilibrium move to the right. So increasing concentration of A will move the equilibrium to the right hand side, and the reason for that is that that will decrease the concentration of A. And we've also got like a few similar kind of scenarios just going through the other options. If I decrease concentration of A, that will in fact move the equilibrium to the left. The reason for that is I've decreased A, the system therefore wants to make more A to replace that, and that will involve the reaction moving in the backward direction. So some B is going to turn back into A, and that is to increase the A that you just lost. Final two cases, if I increase B, it works to the reactants as well. I've now got more B than I had at the start. The system wants to get rid of that, so it's going to move the reaction to the left, the equilibrium position to the left, to decrease that concentration of B. So equilibrium to the left, the reason for that is to decrease concentration of B. And if I decrease B, the system wants to increase it again, so it's going to move it to the right to make more B. One important factor, which again we don't want to get too far into until we get to A2, even though you are officially changing the position of the equilibrium, it doesn't actually change your Kc values. You can prove it using a bit of maths, but we'll not worry about that now. But the important thing just to remember for your exam is that changes in concentration do not actually affect your Kc values for an expression. So that was changing concentration. Changing pressure is kind of a similar level of analysis. And this will involve gas reactions, and this will involve counting the numbers of molecules of each side of equilibrium arrow. We'll just jump straight into the examples. If I have 2A reacting to make B, quick analysis, I have 2 molecules of gas on the left, and in total 1 molecule of gas on the right. So in other words, different sides of the equilibrium position have got different numbers of gas particles. If I change the conditions of the equilibrium, for example, by increasing the pressure, according to Le Chatelier's principle, the system will therefore want to decrease the pressure in response to that, in other words, to do the opposite. The only thing it can do in terms of this equilibrium to decrease pressure is to move the equilibrium to the side which has got fewer gas molecules. If you've got fewer gas molecules in the same space, that's going to reduce the pressure experienced by the system as a whole. So, What we do here, if we increase pressure, we analyse the number of particles, we go to the side with the fewer number of particles, and in this case, the equilibrium will move to the right, because that is the side which has got the fewer number of gas particles. So, equilibrium moves to the right, as there are fewer particles on the right hand side. Opposite will be true. If I decrease the pressure, the system wants to increase the pressure by moving to the side with more gas particles. So in that case, equilibrium moves to the left because there are more particles on the left hand side. They can try and trick you. In this case, the second example, you've got A going to B, that's one gas particle going to one gas particle. In this case, you're not going to be able to have any effect of pressure on equilibrium because your system is not able to either increase or decrease pressure by manipulating the left hand side or right hand side. So no matter what way you do it, there's going to be no effect on equilibrium no matter what you do to the pressure. The third example is to show you that you need to count up actual totals of these gas molecules. Whilst you've got two things on the left hand side, there's actually only two gas particles, but you've only got one substance on the right, but there's four of it, so that gives you four on the right hand side. Once you've analysed that, it's just the same as normal. Increasing pressure, system wants to decrease pressure, which involves moving to the left, where there are fewer gas particles. And conversely, if we decrease the pressure, in other words, the system will want to move to the right to increase pressure back again, so equilibrium moves to the right because there are more particles on the right hand side. The final thing you can do to actually affect the position of the equilibrium is change its temperature, and this potentially can be a little bit of a trickier one. The concept is the same, but they have a lot more scope with different styles of question they can ask you in this example. The Hoteliers Principal still applies the same, no. So in other words, if I've got an equilibrium, such as this, so NO2 going to N2O4, if I change the temperature, the system will try to do the opposite to the temperature. So in other words, if I had this equilibrium set up and I increase the temperature experienced by the equilibrium, my equilibrium would want to decrease the temperature. The only way it can affect the temperature is by favouring one side or the other of the reaction. An important thing to note is if a reaction is exothermic in one direction, it will be entirely endothermic in the other direction. So in the example I just went through there, if I had this equilibrium and I increased the temperature of the equilibrium, my reaction will want to decrease the temperature. The way it decreases the temperature here is by favouring the endothermic reaction, because as you know, endothermic reactions cool down, and that will move the equilibrium to the left in order to cool down the reaction. So it involves a little bit more analysis of the exothermic and endothermic sides of the reaction there. If we look at a couple of scenarios, again keeping nice simple ones just with A and B, they will have to give you a wee bit of information about what side of the reaction is exo or endo, but they can be a wee bit cryptic with how they express that, so I'll look at a couple of examples of those in a second. But nice simple ones here. Forward reaction exo, back reaction endo. If I increase the temperature, my equilibrium wants to cool down. To cool down, it will favour the endothermic reaction, because that will make it take heat in, right? And that will cause the reaction moved from right to left. Equilibrium moves to the left. Equilibrium left, if I increase temperature, explanation would be that favours the endothermic reaction. And we want to do that because that will allow the reaction to cool down. So favours endo reaction to decrease the temperature of that equilibrium. Opposite will be true. If I decrease temperature, the equilibrium wants to warm up, so it moves to the right hand side because that's the exothermic part of the reaction. So we favour the exo reaction to increase the temperature. Opposite will be true. Remember, different reactions can be exo or endo in the forward direction. If I had one which is endo in the forward direction, increasing temperature would actually cause the forward reaction to be favoured to move the equilibrium to the right. And if I decrease the temperature, it'll actually favour the reverse reaction because that will heat it up. It's being exothermic, and that'll move the equilibrium to the left-hand side. So those are your three factors for how you can affect the position of the equilibrium. So your concentration, pressure, and temperature. Just quickly before we move on to the next section, I said they can be a wee bit more tricky with how they actually express the temperature ones. What I mean by that is an example like this. If I take A going to B just as a simple made up equilibrium, something they could tell you is just an effect of changing temperature and ask you to work back to work out whether the reaction is exothermic or endothermic. They might give you that equilibrium and tell you this fact. Increasing the temperature caused an increase in the concentration of B. So there's a little bit of interpreting to do there. They're making it a wee bit cryptic here. Important thing to think is, if I'm increasing the concentration of B, therefore my forward reaction must have taken over, it must be increased, because I'm favouring the production of the product rather than the reactant. Therefore, that means that the A to B reaction, which we're favouring, must cause the reaction to cool down, because the reaction wants to cool down because of increased temperature. That must mean the forward reaction is endo and the reverse is exo. And if I wanted to give a delta H for that, I mean delta H would have to be a positive value. Another thing which I think I forgot to mention was Kc values actually are the only ones affected by temperature. Kc is not affected by concentration or pressure, but you can affect it with temperature. The important thing to kind of interpret that is, if I cause something that moves the equilibrium to the right, in this case for temperature, that will cause an increase of the top half of the Kc expression. It will cause an increase in your Kc value. If I move to the left hand side to favour the reactants, that will cause a decrease in the Kc value. So how they might put that into the question is they might tell you about reaction. Let's go C going back and forward to D. It might tell you that decreasing the temperature caused an increase in your Kc value. So obviously there's a wee bit more interpreting to do here. From what I've just told you, if I've increased the Kc value, the reaction must be favouring the right hand side. So the interpretation of that would be, so increased Kc means right hand side is favoured, the products. That means the equilibrium must have moved to the right hand side. That means that the C to D reaction, the forward one, must cause a reaction to heat up. Why I'm saying that is decreasing the temperature causes a change. If I've decreased the temperature, the system wants to increase it in return. So this must be that heating up to cause it to oppose that cooling down. Therefore, the forward reaction is exo because it's heating the reaction up, and therefore the delta H of that forward reaction is a negative value. So a couple of ways they can make it a little bit more complicated with how they express the information about the effect of an equilibrium change. So we're almost there with equilibrium. The final few parts in this topic are a couple of industrial applications of equilibrium interpretation. There's two you're meant to know about. One you have touched on before GCSE, it's called the Harbour Process. The second one is a little bit new, it's called the contact process. There's a little bit of analysis of why you might pick certain conditions, and then a wee bit of rote learning in terms of what those conditions are. So in the Harbour process, it's the process where you react nitrogen and hydrogen to make ammonia. Ammonia is obviously very useful for making fertilizers. There's nothing too complicated to understand about the chemistry there, it's just two gases reacting. Important thing to hone in on is the fact that it is an equilibrium being set up because that is a reversible reaction. Important thing to note is that that is exothermic in the forward direction. Delta H has a negative sign. And the things that they might want you to analyse are rate and yield of the reaction. Now this involves both what we learned in this topic about equilibrium. Helps if you spell equilibrium right. Because yield, is, if you think about that, that means how much product you make, and that's going to be involving how much do you favour the right hand side. But they can also bring in wee points from the previous topic, which was kinetics, because they want to know about how quickly this reaction takes place. So these final two parts rely on a wee bit of content or a theory from kinetics and equilibrium to understand this fully. So the two factors we have to be able to explain are the temperature and the pressure that you pick for this reaction. Now those are given to you already. The temperature you actually do pick is 450 degrees C. The pressure is 200 atmosphere, which is 200 times atmospheric pressure. You also use an ion catalyst. Our explanation for why we pick that particular temperature is this. If you analyse the reaction here, it's exothermic in the forward direction. What that means is, if I want to make as much product as possible, in other words, favour the right hand side, I actually want to have a really cold reaction, because if I cool down my equilibrium, the equilibrium wants to heat itself back up, and that will involve moving the reaction to the right hand side. So you might think that's great, making lots of ammonia by having a really cool reaction, but there's a trade-off there, or a compromise you have to make. If I have a really cold reaction, I will get a lot of ammonia being made, but it's going to take ages for it to be made, because according to my kinetics topic, a lower temperature will cause a slower reaction because there's less successful collisions. So what we actually do is pick a temperature kind of is in between those two extremes. That's explained here. Decreasing the temperature would move the position of equilibrium to the right to increase the temperature, which would give a high yield, so a high amount of ammonia being made. However, a low temperature would give a very, very slow reaction, which isn't very feasible. This means we pick a temperature sometimes kind of in the middle, at 450 degrees, that gives a kind of an okay rate and an okay yield. So it's kind of best of both worlds. How we would explain that in a question, we'd say we're compromising between yield and rate, because too far to one extreme will cause the other one to be very low. Pressure is the next one. Again, if we analyse this reaction, we've got 4 particles of gas on the left hand side, only 2 on the right. Therefore, to increase the yield of this, I should have a really high pressure, because that will push my equilibrium to the right hand side to lower the pressure. And that is true. If high pressure is used, the equilibrium moves to the right to decrease the pressure, giving a good yield. There is a compromise this time. It's not to do with rate, because actually a high pressure would increase your rate as well. It's to do with the costs associated with that. There is kind of an upper limit with how you can pressurise gases before it gets too expensive, because you actually need to compress them in the first place and need quite expensive pipes to hold that pressure in. So we only go so high, we go to 200 atmospheres, and that's a compromise between yield and cost. So key things here are, you need to know these off by heart. It is 450 degrees specifically for your temperature, 200 atmospheres specifically for your pressure. The ion catalyst we haven't mentioned, the only thing just to be aware of it is, it's not going to affect your yield. Remember, catalysts do not affect like how the forward or reverse reaction are favoured. It just speeds both up. So doesn't affect yield. Just increases the rate. There are a couple of points at the bottom here about how you can actually make it a bit more efficient. So you can, given that this is equilibrium, not all of your nitrogen and hydrogen is going to get used up. You can recycle it to make sure it does get used up eventually. And the other thing is, you can use the energy given off in this exothermic reaction to heat up the incoming gases to keep the whole cycle going. That's not really anything you know in too much detail for the exam though. Final bit then, we've got the contact process. The analysis for it is actually very similar. It's just got slightly different conditions and a slightly different equation. The contact process involves making sulfur trioxide from sulfur dioxide according to this reversible reaction. Again, you notice it's exothermic here. The whole purpose of this is that sulfur trioxide is a precursor of sulfuric acid. Basically, you dissolve that in water and then oxidize it a wee bit further, makes you H2SO4. But this is an important first step in it. The kind of compromises you're doing here are pretty much the same kind of thought process as what we had for the Harbour process. Looking at an exothermic forward reaction, to get a high yield of that, we would be looking for a low temperature, but again, low temperature means slow reaction. Therefore, we have to pick a temperature kind of halfway in the middle there. Luckily, however, the temperature they picked is actually the same as a Harbour Process, so it's still a 450 degrees C. It's a compromise between yield and rate of reaction. Pressure, there is the same consideration again. If you look at the number of particles, there's 3 on the right hand side, 2 on the right. Sorry, 3 on the left hand side, 2 on the right hand side. Therefore, to make more product, we want a high pressure to push it all the way to the right hand side. That would also increase the rate as well, which would be good. But again, we've got the upper limit. If you've got a high pressure, it costs a lot to do that, to pressurize the gases and also to have thick enough and sturdy enough pipes to hold that pressure. Therefore, compromise pressure is used. One thing to notice is, unfortunately, that is a much lower pressure you have to remember. It's not 200, it's 2. Okay, so it works with a lower temperature than the Harbour Process. And the final change is, whilst we had an iron catalyst in terms of the Harbour Process, this one's a little more complicated. It's a specific one you're meant to know about. It's vanadium 5 oxide. So you can call it vanadium 5 oxide. The formula of that is V2O5, because basically it's a swap and drop. Vanadium has got a 5 charge or 5 valency. Oxygen's got a 2 minus charge. Swapping and dropping those valencies will give you V2O5, which is our formula.